Northwestern. Western Oh yeah, this is
We're gonna.
I think USC.
Pierre. I mean, like,
Whoa.
whoa, it's, no, they give you scholarship, yes, yes.
3, 4, 5, 6, 7.
Yeah, they gave me a little bit of alcohol. 6,000 per year. I literally have like.
Okay, so thoughts on this? Was this useful? Was this helpful?
Not that complicated.
Until we hit the red black trees?
Yeah.
So in terms of the 2, 3 trees, though, it makes sense?
Yeah.
Excellent. Okay. So let's just go through a couple of things here. What is a 2, 3, 4 tree? Or a 2, 4 tree? What determines a 2, 3, 4 tree? Dan?
All lengths are the same distance from the root.
So is that true of any B tree? Not just a 2, 3, 4 tree?
They also have like you can't have, like, if you have one key associated with two elements, like 2 or 3, so you have 2 keys with associated values that have 3 links.
Okay.
So 3 children, but you can't have more than that. It's like n plus 1.
Okay, so for a 2, 4 tree, again, so first of all, any B tree, and it's a little bit different in terms of, say the first thing you said first. What was the first thing you said?
All the no links are the same distance from the root.
Yeah, and so the way that the Princeton textbook is defining it is no links, right? So these are all, what's the other way we might say that? What's another way we'd say what Daniel just said? All the no links are the same distance away, therefore.
They have no children.
What have no children? So the leaves therefore are.
Oh, seem,
Yeah, so we've been talking about the fact that all the leaf nodes are the same distance away. The way the Princeton review or the Princeton book talks about it is that all of the null children nodes are the same distance away. Same thing, right? Yes? Okay, cool. But what makes a 2, 3, 4 tree? Mary? So how many children can we have with a 2, 3, 4 tree? Okay. Or 2. Can we have 1? Nope, we can't. So it just literally, it's the number of children, right? So what defines a 2, 3 tree?
2 or 3.
Same thing, right? 2 or 3 children. We can't have 4 children, which makes what's the most we could have in a node? How many keys? And again, they talked about key value pairs. So how many values or how many keys could we have in a 2, 3 tree node? Keys.
Seems like 4 in the middle.
Everyone decide and tell me, because no one's gotten it completely right yet. How many things can we have in a node in a 2, 3 tree?
Thing. 2.
One or 2. Thank you. Yes, we can have 1 or 2. We can't have 2. We can have 1 or 2. Right there. How many things can we have? How many keys can we have in a node in a 2, 3, 4 tree? There we go. Excellent. Okay. Invariance. And he talks a lot about invariance. First of all, what do we mean by invariance? What is an invariant? Therefore, when we talk about invariance, what does that mean? Okay, so it's a constant to do, right? It's kind of the rules of the road with these things. Okay, so everyone take out your piece of paper again. Take out a piece of paper. I won't make you do the first one because what happens when we add 1, 2, 3, 4, 5, 6, 7 into a regular BST? It's the spindly one, right? 1, 2, 3, 4, 5, 6, 7. Yes?
Yes.
With a regular BST. So try doing it into a 2, 3 tree. Yep. Yep. Yes. Paper's too wide. Anyone else? Favorite? Yep, we know what, you hopefully know what the top one will look like. If you don't, do it on paper, but. And this one, is this one gonna take a lot of reorganizing every time you write it? Yeah, a little bit, yep. You could theoretically try and conceptualize it otherwise, but I wouldn't. I would just draw them out in steps. L is the limit. Do we want to do these on the board? Do we want to get up and do this on the board? All right, everyone hop up. We can erase that. 1, 2, 3. Jack, you can join these two guys. Tony, Daniel, Mary, and then you three. Marker. Jackie, you're with those. Tony, Daniel, Mary. You guys go to that side.
Can we erase it?
Yeah, you can erase that.
So.
Does everyone have a marker?
We need one. Yes. We built up.
Oh.
We built up.
I think it's passed.
Not really.
Yeah, start with 1.
Not the middle one. Oh, okay. One.
So what do we pass up when we have a 2, 3 tree?
Oh, the left middle.
With a 2, 3 tree.
Middle, yeah. The 2, 4 trees, the one.
Correct.
Yeah.
Yeah.
My bad.
You're good.
Maybe. We don't need.
We can only have one.
Or you had one.
Because 4 is greater than 3, but 6 was greater.
And that's 3. And when you add 2, it's here, right?
Yeah.
You add then 2, there's almost no more 3. No, that's the middle one.
3 down.
Yeah. Yeah, that's 2 and 4 here. Wait, no 5. So it's 2 and then they're together, but there's no space. So we'll make a 3.
I don't know, but usually like right?
Oh,
Starting.
Just don't move it before we draw it. Just draw 1 and 2 and then put 3.
Is that first step correct? Just making sure.
You see if they can figure it out. You shouldn't be doing it anyway, Jackie. These two should be doing it. You can consult, but no. Yeah, no, just hand it back.
Plus 3 is or is maybe
Maybe
here.
like separate group, right? Like the way we did it.
So
1, 2, 3.
It's a 2, 3 tree.
Anyway, wait, so the
Hey,
base.
here.
2 and 6. And then we have 4.
Yeah, so.
Like 4 versus 2. That's not
Make sure everyone's participating.
right.
There
We have 2, so just add first.
Oh.
Okay, well, because there's 2, 3, around 1, 2, 5, 6. Then you would hit.
It's
Yeah,
in
and then 5. That's not there's 5. You would add
5.
So then the
We can
four
put
goes
5 is here for the.
No, but the thing is moving up, 7 is staying down. Right?
Yeah, that's cool.
4.
Oh,
So don't we connect?
Wait, no, I don't think so.
4 goes down.
Oh, yeah, because we need to.
Can you have a leaf? Can you have something that has one child?
I was gonna say, this, these are connected.
Why was the 1 and 3
Four.
1 and 3, 5.
One and 3 goes here,
Oh,
one
it's
here.
just put them both places together.
They both go.
Like-
Yeah, like, what is
Uh,
2, 5?
yeah,
4, and 6.
Yeah.
Four groups, what's next?
And
6.
Yeah, but now they're all the same
Yeah,
distance,
so-
but they're.
6 goes to small.
4 and 6.
Right, 6 on this side.
Fine.
So that you use.
Yeah.
So 5 is 7.
Oh.
That's not two, right?
Yeah, but.
But we have to make it all two, or.
But this is limited. So we can't have more than 2 things.
But we can do one. Oh, that is the one, so I think it was, 4 and 4,
Yeah.
5 and 7.
5, 7.
They're exact, that was.
They
both seven, yeah,
6. I think some of it was like.
What do we know about our leaf nodes?
Must be the same height.
They have to be the same height.
Like, if you.
Yeah.
What do we know about our leaf nodes?
Yeah,
No,
but they're in this
3,
they're
add 4. Right? And then we add 5, and then 4 goes like.
They should have the same.
So 4. 2. That's 1.
does that look right? Just look at it. Does it look right?
Well,
I mean,
So
does-
minus.
okay, should the root have more than one?
Should it? I can't answer whether it should. Jackie, give the marker back. Yeah, you can just keep going from what he's got.
No, we have to add this difference. Like, I'd say the 3 goes in 6. Wait, no, 3 has to
No,
go
3 has to go with
because it's less than 4.
Now we're on 6, right?
Yeah.
6 goes here.
This makes sense, 6 goes there.
Yeah.
Oh, yeah,
Now-
I'm not sure. Yeah, 7.
7.
no,
Here, so 6 goes up, right?
Like above 5. Then we're back in the same.
No, no.
Yeah.
No, you're right.
That would have been an issue because it have one.
Isn't that same as the
No, it's 7 goes,
maybe like 2 goes
Well,
up.
it depends on the order
Two
you
goes
have.
up.
No,
You wanna put 1 tip,
uh,
then have 3 going.
always, this doesn't work. No, you can't, you don't put 7 here because you need 3 children below 4, 4 and 6. So you put 7
Okay,
here.
I'll give you a hint since you guys are saying it. That's not right.
Okay.
We end up.
Oh, then I guess you did a whole thing wrong.
So.
Yeah.
It's 3.
Three,
You end up like
Three.
five.
Can I try and fix that?
No, wait, this is where, this is where.
I think this is. But they're separate. Yeah, they're separate. Right.
Well, 2, 3 trees is only.
Because
Five standards doesn't matter what the root is, the root will be 1. Right, and if you don't have 7, I mean.
That's we're going.
Does the root has to be like 2 for it to be treating it sides, you have.
Like 2 things in it?
no,
No, yeah.
no, you don't put it out.
Yeah, we can have 1 thing.
Because
Are you saying?
when you have 2 and 4 as the parent, you need 3 children, so put 5
Yeah.
as a child.
It's
Yeah.
No.
Yeah.
No, the 4 still stays.
I'll give you another 2 minutes.
You can't put 2 out. Yeah, right. Yeah,
Doesn't work.
And now, as 6 goes here, now there's no space. So 4
Yeah.
I'd say it's 4 goes up.
Where's the?
Can we use the middle for the root?
Can you use the middle for the root? What does that even mean?
Like the,
No,
you know, like the,
The median?
oh yeah, the median number as the root.
I don't know what that means. What is the median number?
Like
4.
You're adding them in this order, 1, 2, 3, 4, 5, 6, 7, in that order.
Like, can we like restructure it?
Oh.
No, you're adding those things in that order. Does a 2, 3 tree restructure by itself? Yes, it does.
No. Why is 2 on top? It shouldn't be 10. We add 1, I'm gonna start with that. We add 1,
I'm sorry, it's not. But.
and then we add 2,
Yeah,
okay, and then
we had 3, 2 goes up.
we add 3. Oh, 2 does go up, right?
Yeah, 2 does go up.
Yeah, 3 plus 2. So we add
No,
two.
just say that's not it.
We're split.
And then we add 4. 4 plus go here.
Yes.
We add 5.
Yeah.
5 has to go
Yes.
here.
Okay.
We got 6. 6 must go here.
Four goes up.
No, wait, 6 doesn't go there. What do you mean? Because when you add 6 here, it messes up the nodes. I mean, yeah, the children. You need
Everything here, oh, you put 6 over here.
yeah, you probably put 6 like here or something.
No, don't put it after it, just put 5, 6. We have.
Oh, we put 6 here.
The 3 or 5 is all.
And
And then put 7 here.
No, you put 7 here, 6 goes up.
Yeah, 6
Oh,
goes up.
right, so
That goes to the-
here, this becomes 5 and 6.
You put 6.
6 goes in here and 4 goes up.
Yeah.
Well, okay.
No, you just copy the answer from
Yeah,
the
right.
from the last step.
4 goes here. And then 7.
No, I.
6, that's 6.
Oh, yeah, 6.
go up.
Yeah.
You didn't show us how you got there.
No, but I did, I was doing it.
No, you just throw the 7
No,
up.
I didn't, I did it just 1 second.
Okay, and then this becomes 3 and 5 and this becomes,
Right.
right, like
No,
that.
5 gets connected to 6.
What I, that's what I did.
Everything has to happen.
No, 5 cents, yeah.
5 connects to
Oh,
6.
yeah.
2 connects to 3.
2 and 6 are separate.
Yeah, 2 and 6 are
Yeah,
7.
right, you're right.
Start 6 then.
Like that, like that.
No, you didn't write that 7 step. You just wrote the 7 up there. I tried to go with 7 over here. That's all.
No, because I realized that it's
Yeah, but
it's not less than 6.
Two steps.
I realized it's not less than 6. No, I did it in my head.
I know the answer like that, of course, because it has to be balanced, the middle one has to go in the middle, of course, that's the answer. They literally go to step.
What is?
Again, I already saw this.
Okay, let's take a look, because we have a cool little thing here. And the cool little thing we have here is this. All right, this is a really cool visualizer, so we're gonna add one. Oops, no, we're not, we're gonna do that, we already had one, we're gonna add one. Where does 2 go? Goes in the same node, right? If we have 2 things, that's what we get. Now, when we add 3, what's gonna happen? 2's gonna go up. Boom, there we go. When we add 4, where does 4 go? Next to,
Next to 2.
next to 3. It has to, it can't go up here yet. Okay, so 4 has to get out of here. When we add 5, what's gonna happen?
It goes next to 3 and 4, and then 4 goes up. to 2.
Yes, it'll get added to this node, but it's a 2-3 node, or it's 2-3 tree, so 4 is gonna go up. There we go. Now when we add 6,
It's gonna be with 5.
gonna be with 5. Now, is this all fine so far?
Yeah.
And you'll notice that every leaf node is same distance, so we're good there. And we add 7. What happens when we add 7?
6 gonna go up, and then 4.
7 goes here, 6 goes up. Now we have 2, 4, 6. 4 goes up. 4 should be the root. Bam, there we go.
Yeah,
Okay.
yeah, so we're pretty close.
Okay. Only works in hand grenades. Okay.
Very close.
Okay, so when we do that, this is what we get. Okay. What does that bottom look like?
That.
What kind of binary search tree?
Yeah, linked list. Binary.
That looks like a linked list on the bottom?
No, look, you have like different elements in a node. You have many.
Yeah, there's more than one thing in each of those nodes?
Yeah, so like they.
How is there more than one element in each of those nodes?
Oh, never.
Yeah, okay. I want you guys, I totally want everyone to participate, but give like a half-second thought before you throw out any ideas that you might cross your minds, okay? So what does that look like on the bottom? A perfectly bushy binary search tree. What are we after? What are we trying to get to? Like, what's our goal with a binary search tree? To get it to be that, like be a perfectly bushy binary search tree, right? So that's the goal. And we added these things in exactly the same order. Make sense? Yeah. Okay, cool. So we're done. Not quite. Okay. So back up try to come up with an order where if you add items 1 through 7, you get a height of 1. What's our height here? 2, right? We have 2 links from our root. Try and do this to get a height of 1. Back up, you can erase what you have. You're trying to get a height of 1.
Wait, it's 3 tree, right?
This is a 2-3 tree with a height of 1.
I can try and write this on paper.
Sure.
Oh. We're gonna make the table.
Let's give Gordon someone to work with then. Someone, one of the other groups want to volunteer to work with Gordon? Because Alex is doing it on paper.
No. Wait.
Actually, Alex, you just have to communicate. Okay, or you can switch, whatever you want to do.
Same thing. Two, three, because of height of
Height of 1.
So like one.
Yeah.
Yes.
Height of 1.
No. Yeah, so we can.
Oh, we coming up the list of orders, we're going broad, like, we all there's, we're just fine. Like, well,
Two numbers on top.
yeah, let's go in order. So we do first draw the routines. What is it? Yeah. No, 4 step 2. Wait.
1, 2, okay.
Oh, it was made to. Oh, it would be 1.
Okay, I know this is 1, 2, 1.
And then one in the root.
Yeah.
One would be this one. Yeah, we want it to be 4 and 5 and
3.
You can only have 2.
No,
You can't have 1.
Yeah.
2, 2,
Oh, that's-
1, 2,
Let's
2.
think about the order.
Okay, so we would add the.
So here, wouldn't it be, you are gonna have 2 things on the one and then 3 things on the bottom. Think about like, correct?
3,
Or
1, 2.
and then the 1, 4, also 1, 3, 4, 7, all these times. 6, 7 here. Like,
We're missing 2.
yeah, 5.
So that would be added.
Yeah, we have to start out working, right? So then we get 2, and then.
Make sure you keep track of the order that you're adding them. So I can see the order they're adding. Don't just show me the tree. You gotta show me the order you added them in.
Okay, so.
Yes.
Only 3 monsters.
Oh, yeah, you're right.
Now figure out the order.
Yes, okay, yeah, that works.
You can just do comma separate, yes, that.
Do it in order 4, I think.
If it works.
Yeah, exactly.
All right, so then you're going to test it. So on the home page is a link to this thing at the very bottom of the home page. So go to,
Goes out 5.
you don't all need to do it, but someone in your group needs to do it. Visualize 2, 3 tree right there at the bottom. Click on that and run your numbers through it, see if it works.
Don't we have to 1, 3, 4, 2.
You can't, right? You know, if you do it 1 through 7, you know the tree you're gonna get, so you can't do it in order.
Oh, okay, so.
It has, you're trying to figure out an order that you're adding them, so you get a height 1.
Oh, and order.
An order. Yep.
Right.
It will not, you know, you can't get it from 1, 2, 3, 4, 5, 6, 7, because we gotta.
Would be as a 1, 3, 6 of the 4.
So 2, 3, and 5. How about that? And we have 3, 5.
5 was that.
1, 2, 3, 5, 6, 3, 5, 7. Or 6. Or 6.
You can't add 7, because 7 has no.
No, we don't have a 4 yet, but 2, 3, 5, that's like that. If we add 6 or 7.
Oh, I know.
6 and 7.
Got it. I got it.
Oh, okay. Oh, we have 7.
Right.
And we had 4. And we had
5.
So the house we have.
So the value will.
2, 3.
5, right? Yes. Right, this, you would add 2, you should reach 5, right?
add 6 here.
6 goes with here.
And 7 goes with
7 goes with here. 6
That's
goes
it.
there.
We add 6, 7. 6 is up there.
No, 6 goes.
Right, 6.
Yeah.
And 6.
No, but then it doesn't make sense. Like, add 7 improves 6.
The middle one goes up,
Right, 6 goes up here.
And then.
well, if 6 goes up, 6 connects to 5 and 7. 7
is, right?
Oh, 5 is supposed to be connected to
Right.
2.
Right.
So now, definitely, yeah, so now we have 3 in the
Yes.
Wait, or you can just put like, well, you can just put like 4 here.
Yeah, so.
And then we add 4, so the 4 goes 3, 5, over here, right?
Yeah.
4 has to go to 5. Or going in,
Oh, 4 has to go.
and then 1 goes to That's 1.
Well, 6 to go up. But if we add 4, then 6, 5 to go up.
Yeah.
And this is. Five and 7 can't be 2. Then you split it. Test it.
What should we add?
Test it out, see if it works.
5 would go up, right? But if we had 4, 5, 7, 5 still wins. It's a 2, 3 tree.
Oh, that's 6.
That's why it's good to come, do a little review.
Yeah. But now I kind of get it, you don't know these stories before it goes like up.
Yeah, I mean, the one key, I think of it a little bit differently. Because everyone is drawing the right tree. So what's the one thing that you need to go up into the root?
That you fill in a leaf.
Well, what number is the key number to get into the leaf node? Or into the root node?
We have 4 items. 6 went up. 4.
Leaf node?
Into the root.
Oh, okay.
What's that?
You don't have to have 3.
Yeah.
3. Once you get 3 into the root, you're fine. You could, so yeah, you either need to get 3 or. Or 5.
It has to be 3 because for a tree like this, it kind of goes in order like that.
Yeah, I don't, can you get?
So this works.
It does, so 2 goes up,
You have like 2 and 5.
5,
Oh, yeah, if you have.
That's 3, 6, 5 goes up.
And there's 6, and then you have 6 and 7.
Oh, 6, 7.
Yeah.
Like, so you could have 2 here, and then we have 5,
Oh,
you could have
Oh,
3
yeah.
boxes.
No, yeah, this also,
Yeah.
yeah, 2 also works, because 3 just has 4.
Then you'll have,
Same thing.
Wait, but then.
Two things in the root,
Well,
regardless, you have to have 2 in the root.
Yeah.
So 3, 4, and 6.
It works.
yeah.
They have the same thing.
Yeah, that works.
Oh, maybe like.
Actually, does it work?
Let me think about it, maybe 3, 5, 1, 2, you do that.
6, 7.
6, 7,
Yeah.
and then like
We had 1, 3,
1,
4.
3, 2,
1.
and then at 4. No, at 6 and no, let me see. Oh, you did, you added 6 and then 5, then it would, so we get 5 with the 6, no.
Yeah, I did it myself. He's right.
No, if you had 6 and then 5, then 5 is
5
middle,
goes
so
up.
5 goes up, and then. Oh, yeah, 6 and then.
2 and 5. 5 in between. So 5 goes up to 9.
But you have 2 and 6. No. Yeah, and then you just put 7 at the end and then 4, and then 4 is put the 2.
Bro, you can't have 1 and 2 on the 2 sides of 3.
Yeah. Wait, let me.
All the things on the left have to be less than its parent.
You didn't have to go to like the very bottom and put 1.
Wait, no, it's like this, yeah.
So do 2, 3, 4, then worse.
2, 3, 4.
That's gonna push.
Oh,
3
yeah,
up,
it should be like 1, 1, 3, 4 first,
or that, yeah.
and then. Oh,
And then you can just add 2. 2 goes on the left side.
and no, yeah,
So
but eventually
it's less than 3.
yeah, 2.
6.
2,
And then you add 2, 3, 5, and 6. 5 goes up and then you.
But you have 4 and 6. I see how to do it. I understand how
No,
to do it
4
now.
and 6, and then.
Alright, you guys sit down and try your numbers in the visualizer. Daniel, Mary, have a seat, try and figure out, get those in there.
Like that?
So what were your numbers? Go ahead, Tony, talk us through it. What you got? What are your numbers? How'd you add them?
Kind of confused. First
Yeah.
of all, we add, this is kind of the structure we're trying to achieve.
So what were the numbers you added?
So we add 1, 3, 4, so.
Okay, 1, 3. So there's 2 keys to this. As soon as you get 3 up you should be good to go. Right? Because then what do you want to add? And then we have a whole bunch of different options. What can I do from here? Sure, we could do two. Two will end up over there. That works. Then what?
And add 5 and 6.
Yeah, 5 and 6 is fine. Because what will happen with 5 and 6? 5 will go up,
And 7, yeah.
and then we add 7.
Yeah, we were right. No.
Well, there are, how many different ways are there to do this? A lot, yeah, multiple, probably not infinite, no, but there's a lot. There's only 7 numbers, so it wouldn't be infinite. But as soon as you get 3 up in there, you work there. You did 1. Logan, what'd you do? You did 1, 2, 3. So 2 goes up, and then what though?
I did 5, 6.
Okay, 5, well, 5, 6 won't, okay, 5, 6. So 5 goes up,
Now I did 4, 7.
4 and 7. That 2 works,
I did a different.
okay? So you can see, like before, we had 2 things, 1 thing, 2 things. Here we've got 1, 2, 2, that works. Alex, what do you had?
I did 1, 4, 3, 6.
Hang on, 1, 4, okay. This is virtually the same thing we just did, because the one in that just ends up being the same.
6, 5.
Yeah, you're doing the exact same thing we talked through, just backwards. That's fine.
2, 7.
So you're gonna end up with the exact same structure ultimately as whatever, I think was Tony that was talking through this one. You just,
What do you mean backwards? He did like 7, 2, 5.
well, how could we do, you did 1, 5, 4, he did 1, 4, 5.
That's the same thing.
It becomes the same thing because of where they go. Obviously, the order is different, and that's why we have lots of different multiple orderings.
5.
Okay, cool. So we're comfortable with that, hopefully, right? So 2, 3, 4, 5, 6, 1, 7, another one. Always bushy, right? And this is actually better runtime than adding them in order, right? So that's good. 2 invariants, all leaves must be the same distance from the root. We know that. A leaf node with k items must have exactly k plus 1 children. Okay. So the tree below is impossible. Why?
Different depth.
Different depths, right? So different leaves with different depths. We can't do that. And this has,
Oh, that one has.
is this structure okay?
Yeah. No, the 2, 3 tree. Yeah.
Well, if it's not, but as a B tree, it works because I've got 1 item here and it's got 2 leaves. What about this one? Bunch of different reasons it doesn't work. One is it's different distance away, and the other thing is what?
It's 2 more children.
Yeah, if I've got 2 things in here, I need 3 children. Okay, so that's another piece of this that doesn't actually work. Okay. Okay, worst case performance. What is our worst case performance? What's our best case and worst case performance with these things? Log for virtually anything we're going to do with these things, right? Contains. Contains. Oh, yes, but let's say contains. It's log n, but so we can see that it is ostensibly somewhere between log of L plus 1 and log of 2, right? Because our best case and our worst case, what's our worst case? We have 1 thing in each node ostensibly, and our best case is we have 2 things in every node. Okay, what does this ultimately reduce to in asymptotic analysis? It's just log, right? We don't really care if it's log base 2 of n or log base 3 of n, right? It's just log n.
I still understand why it would be log base 2 then.
Oh, if there's like 2 items in each, no.
So if I have 1 item in each thing, the best case in a straight binary search tree, not a B tree, is log base 2, right? But if I can put 2 things in every node, I get log base 3 event.
Because each time you have 2 things connecting them down, and you're essentially dividing it by 2 every time, so.
And I have, right, so I've got one thing has 2 connections, one thing has 3 connections.
So,
I have 3 children because I got 2 things in the
so
node.
if you could put 3 in, it would be more than 4 of them?
N plus 1 or L plus 1.
Oh, yeah.
Oh, all right, everybody, have an awesome time. That was not nearly as far as I expected to get.
You also get to go?
No, Okay.
No way.
track.
Oh, yeah, I got, I'm not getting that right now. What, how was that? Alright, where are you running?
Yep. Hey, good luck. Have fun. Jump high, run fast. All those things. Okay, so we're gonna try and crush through the rest of this, and then get to watch the video. Okay, so there's that. We don't care. Do we really want to do BST deletion? No, I don't think so. We could. B tree deletion. Okay, so we're going to jump over. No, we're going to jump over here. And see how we do with this. Okay, which of the following are valid 2-3 trees? And you can write this down on your piece of paper. So question 1.
Can I get a new piece of paper, because I kind of did a lot of.
All of your stuff on there?
Yeah, all my thinking.
There you go. Valid 2-3 tree.
Is this number 2?
This is, well, isn't it question 1?
Oh, question 1.
We did the first one on the boards.
Valid 2-3 tree.
There's more than one.
None of them. Bruh.
Bro, what are you guys talking about?
A is 100.
They're quiet. There are valid 2-3 trees on the board. And there could be more than one. Which of the following are valid 2-3 trees?
Definitely C.
Right? Yes.
C looks pretty good.
C looks great.
They have like, I, odor.
Tony, just write down which one of those you think are valid 2-3 trees. Okay, then write down none. Question 1, none.
Like E.
None of the above. All right. Are we good with this or no?
Yep.
Okay, question 2. Draw 2-3 with the results from inserting 1, 2, 3, 4. We already know what that looks like. Yeah, we just did that. Let's look at what problem 1 looks like on here. Which question was it?
Crazy problem one.
Problem 1, okay. There you go. Suppose we have the following BST. Given a valid, oh, wait, we've done this one too. Yeah, it is. Why is it giving us that question again? Problem 1 of the spring 2018 midterm 2. All right, we're not gonna do that one either. Does everyone remember what it does? I'll give it to you anyway. Given a valid tree that results from deleting the 7 using the procedure from class, Hibbert deletion. We did, so hopefully you get it right. Because we talked it through too.
Just draw it out.
Just draw it out. Nope, draw out what the tree looks like after you delete 7. Oh, okay, wait, here. This is, I think this is what they were looking for. Draw the 2-3 tree that results from inserting 1, 2, 3, 7, 8, 9, 5 in that order. We'll do that one too. All right, so do this one first. So question 2 is our Hibbert deletion on this thing. And then question 3 is draw the 2-3 tree that results from 1, 2, 3, 7, 8, 9, 5.
It's Hibbert deletion.
deletion, the one we swap things around.
C, you don't need it to be, no, we don't know B yet. And C, yep. Well, A and C, yeah. Yes, I do.
Let's go over the answers.
Yep. Yep. Yes. You tell me, is it better? Yes. It's easier to read. For sure. All right, so we'll start with this. Everyone's got an answer to this, yes? Okay. So, we'll go backwards. Is C? Clearly not. Why not? Height, right? We've got, this only has one length, these all have two lengths, okay? Height of two. How about D?
21.
What do you mean 21?
Should only be 2 children.
Yeah, only one thing in the node, it can't have 3 children.
We can choose one to one, right?
That is correct?
Yeah.
Yeah.
Okay.
Okay, so C, no, D, no, B?
45. There's 3 elements.
There's 3 things in here. It's a 2-3 tree, can't have that. Okay, you can only have 2 things. A?
Right.
Yeah, right.
A is correct. A is a valid tree, right? I've got 1 with 2, 1 with 2. This one's got 2 things, it's got 3 children. All the same distance apart. Okay, okay. This thing. Now this is a little bit tricky. So what is Hibbert deletion? What's the idea behind Hibbert deletion?
Take the successor and place it where the name.
Yeah, so we're going to grab the successor, right? And we're going to put it in the root. the picture's a little bit funky here because what's the actual successor to this thing?
No, eight.
8.
But I thought last time it was stuff in the middle there.
It was. Is this picture drawn accurately? Not really, not that way. What's the next number after 7?
Eight. Oh, that's all it is? It's not the one in the middle between the two?
Right, because if we drew the tree differently, right, that would be the number that comes next.
Oh, so we just 8 and shift everything up?
That-
Oh.
Yep. So if we look at the actual answer to this thing, right, we have 2 different answers. You could have taken the predecessor according to this. So if we shift up 8, it just looks like this. If we shift up 5, because that is the, what's the 5 called? The predecessor, so successor, predecessor, either one works. What's up?
So when they mean successor, they don't mean the next thing that's in the middle between the, like the.
If you draw the picture correctly, it will be,
Okay.
okay?
I picked 10 because last time we circled both.
Yes, yeah, right, because you'd think that, okay, it's this thing that's sticking out over here.
Yeah, where is it the smallest element on?
It's the smallest element on the left-hand side. Or the biggest element on the right-hand side, that's all it is. So it's the smallest element on this side, 8. Okay. And essentially, how do we figure out what's the smallest on the right-hand side?
Just by going like. Oh, wait, it's just no. So there's one on the right hand side.
It's the first one
This one. Left.
without a left child. Right? That's essentially what it's gotta be. And if we drew this picture right, 12 would be way up here, then 10, then 11. Does that make sense, Daniel? If we were doing them sort of in order?
Yeah.
8 would be here, 12 would be way out here, 10 would not be the thing that's in the middle. Just because it's not there. Okay, let's be a little bit creative with the 1, 2, 3, because you can look at this, hopefully you start to get a sense. What's gonna happen to 1, 2, 3? 2 is gonna come up. So I know 2 is gonna be in the root. And then 7 gets put where?
Next to 3.
Next to 3, and then 8, next to that, so what comes up? 7 comes up, right? And then I add 9, where does that go?
Right, 8.
Right of 8, and 5.
Next to
Yeah, and I mean, that gets a little bit messy in there, but you should know that 2 and 7 are in the root. And we end up with 2, 7, 1, 3, 5, 8, 9. Good?
Yeah.
Excellent. Okay, so here's what we're going to do. We're going to try this thing. I thought I've dropped a link in here, but I'll put it in now. I have no idea whether or not you all will be able to solve this. You can do it in teams of 3. So why don't we just do this? Why don't we just collapse? Jackie and Alex just move that direction. Coding wars.
What is this thing review?
I'll show you. You're gonna have a war. No, you're not gonna have a war. Oh, sorry, coding game. I called it the wrong thing, but we're just gonna leave it anyway. You may have to log into this thing. It's called Shadows of the Night. And so you're doing a 2-dimensional array. You're Batman jumping around a building trying to save somebody. The goal behind this that uses theoretically. Either way is fine. It doesn't matter. Theoretically, you are. Whoops, come on. Shadows of the Night technically is binary search and 2-dimensional arrays. So maybe collectively you guys can solve this. We'll see. Binary search and intervals. See if you can figure it out.
Binary trees of intervals.
When you guys, I'm assuming, I think you guys have to log into this. It's a good thing. Coding games are worthwhile. Go to the bottom of our homepage. Reload it. Oh, did I not save it?
Oh, Coding Wars.
Coding Wars, yep.
And yes.
Even though it's not Coding Wars, it's Coding Game. Yep, solve it. Collectively, you guys can solve it.
We have to sign up.
You do have to sign up for this one. Don't pay for anything, but you can, this one's actually a really good website just to mess around with. They sort of do similar leak code things, but they gamify it a little bit.
Okay.
So it's kind of fun.
We should use our personal.
Up to you. I would, just because that way, when you leave here, you'll still have access to it. All right, with that, I'm going to,
Well, that's so complicated.
how do I get back to,
Austin.
But, John.
all right, how do I get my, come on. Someone help me out with Zoom. How do I get back to the screen? I eliminated the screen. Now I can't get back to it.
Which screen?
I'm in Zoom, but normally when I go here and I click back to meeting, it kicks me back to like panels that I can get out of it. And nothing's happening. That? Oh, no, there we go. Okay, thank you. Top meeting. Okay, stop.